In this video, we're going to start talking about how pH works, and we're going to start by talking about something called the ionization of water. So here's the problem. Since water can act as an acid or a base, in theory, if you mix water with water, some of the molecules might behave as an acid and some might behave as a base. This technically is an equilibrium, but it is very, very much so in the left direction. This is way more stable than the other side. But if this is an acid, it's going to give up an H plus and you form OH minus. And if this is a base, it's going to receive an H plus and become H3O plus. Okay? So the way we typically write the reaction is, if this was an acid, we say Ka. If it was a base, we say Kb. Either one's technically right. Because this is water, we call it Kw. And these are both liquid. So our Kw is products over reactants. It's literally just these two things multiplied together. So most people write the acid first. It doesn't really matter. And the value for this is 1.0 times 10 to the negative 14th. Okay? This equation, this Kw value, will come up occasionally throughout this chapter, so I figure I should explicitly mention it. This 14 is why the pH scale goes from 0 to 14. We will talk about that in this video, but just not immediately. Okay. It turns out if you want to figure out how strong an acid is, essentially what we're measuring is how much H3O plus there is. And the equation is not difficult, but it does have a logarithm. It's the negative log of the concentration of H3O plus. So, we've briefly mentioned logarithms before. I'm going to try my best to explain this again. It is a negative logarithm. So the logarithm part means every time you change a number from like pH of 2 to pH of 3 or pH of 3 to pH of 4, you're changing by a factor of 10. That's what the logarithm part means. The negative part means that lower pHs, like 1 is more acidic than 2, which is more acidic than 3, and so on and so forth. Okay? But if we have a strong acid, so basically, if you have strong acids, this is pretty straightforward. Let's try an example. So we want to know what is the pH of a, I'll just make up a number, 0.0017 molar HCl solution. Okay. In the last video, we talked about how HCl is a strong acid, which means it completely dissociates. So we don't necessarily have to write the equation for this, but I'm going to, for this example, show it to you. Because everything goes forward, there is no reverse reaction as far as we are concerned. Whatever the concentration of this is, that's what the concentration of this is going to be, since it all goes forward. So this was 0.0017 at the beginning. All of it went forward and became this, so this is also 0.0017. So, to get pH, we take the negative log of this concentration. pH does not have units, but we're assuming that the concentration is in molarity. Okay. So, diving into the calculator, basically covering it up here. Negative log. So not natural log, regular log, log base 10. We are switching from natural log to regular log for quite a while now. Okay, times 0.0017. Hit enter, and the answer comes out to 2.8. So our pH is 2.8. Yay! Not real tough, but we haven't done much with this, so we don't really have a sense for like whether that's a high number or a low number or crazy dangerous or whatever. Okay, but this is a pretty low concentration. Okay, you would expect this is probably not going to do much damage to you. We've used 1 molar HCl or 6 molar HCl in the labs. This is 0.002 basically. Okay. Well, let's try another variation on this. We want to know what is the the concentration of HNO3, which is also a strong acid, if the pH equals, I don't know, 1.85. Okay, so this time, and HNO3 is a strong acid, so we can assume that it completely dissociates. We want to know, if we have the pH, what is the concentration? So for this, pH equals the negative log concentration of H3O plus, but in the same way that this worked, for every one of these HNO3s, we're going to get one H3O plus. So if we can solve for H3O plus, it's the same as this concentration. Okay, now the math's going to get a little difficult because we have to get rid of that logarithm. Before, we just plugged it in the calculator. Now we got to get rid of it. Okay, in terms of what order do you attack things, we've got to get rid of the negative first. Actually, let's plug in the number. So this is 1.85 equals the negative log of the concentration, basically the thing we're solving for. I'm just going to make it x to make my life easier. Okay, first thing we're going to do is multiply both sides by -1 to get rid of this negative. Okay, to get rid of this log, natural log we use e to the x, regular log we use 10 to the x. Okay, same thing as on your calculator. So it's 10 to the whatever on both sides. This cancels out, and x is equal to 10 to the -1.85. The negative is critically important. Please don't forget to type it in. So our concentration of HNO3, which is essentially x, is equal to 10 to the -1.85, and we just plug that in our calculator. So 10 raised to the -1.85. Okay, and I got 0.0141. I guess we have 3 sig figs, we'll do that 3 sig figs. 0.0141 molar. Okay. So, if you have a strong acid, these are like, there's only two variables in this equation. It's either the concentration or the pH. If you're solving for pH, you plug in the concentration of H3O plus, take the negative log of it, there you go. If you have the pH and you're solving for concentration, you're gonna have to get rid of the negative and then the logarithm to solve for this. Okay? As you may have guessed, pH, for some reason, has become the dominant answer. It's the one that we always solve for. We always solve for pH, even if it's a base, which doesn't make a whole lot of sense, but it is what it is. So, because there is pH equals the negative log of H3O plus, there is an equivalent answer for bases called pOH. And this is equal to the negative log concentration of OH minus. Even a compound that doesn't produce OH minus, in the presence of water, will rip an H plus off of water and leave you with OH minus. Okay. So, I guess let's try an example of that, just so you have one in your notes. So we want to know, what is the pH of a, I don't know, 4.7 times 10 to the -3rd molar KOH solution? We said for strong acids that there were 7 to memorize. For bases, if it's a salt that will dissolve in water, potassium always dissolves, and OH minus is the anion, then it's a strong base. Okay, so we want to know what is the pH. Well, we need one more piece of information. It turns out that the pH plus the pOH equals 14.00. Not going to go through all the legwork, but it has to do with taking the negative log of KW and whatever. Okay. So, if we can solve for pOH, we're going to have to subtract it from 14 to get pH. But this is a base, so pOH equals the negative log of 4.7 times 10 to the -3rd molar. Okay. Just made this problem up, so I'm going to have to actually plug it in here. Negative log of 4.7 e to the -3rd. Okay. And I got 2.3, I guess, I only have 2 sig figs. 2.3. Great. Okay, that's a number. The pH is going to be equal to 14 minus that. You'd have to subtract pOH off both sides to solve for pH. So it's basically equal to 14.0 minus pOH, which we just solved for. So 14.00 minus 2.3. So 14 minus 2.3. Okay, I got 11.7. So let's kind of discuss how to tell whether you have an acid or a base. Like, how does the pH scale work? Okay, so we said that this is a base and we got a value of 11.7. Is that good or bad? Does that make sense? Is that a reasonable answer? Who knows? So let's try it. Okay, so let's talk about the pH scale. I'm not going to go into horrifying, excruciating detail, but I at least want to mention this. So typically, the way the pH scale runs is it runs from 0 to 14. I will tell you that it is possible to get pHs above 14 and below 0. But 99% of the time, you're going to be in this range. 7 is neutral. Okay, I'm going to kind of label some things as we go. I didn't space that nicely, but sorry. So this is inherently neutral, and this is defined by the pH of water. So if you have distilled, deionized water, just H's and O's floating around in there, your pH will be 7. As you get a lower number, I guess I could label this pH. Okay. As you get a lower number, this means more acidic. As you get a higher number, this means more basic. Okay. We, by default, as a planet, decided that pH was the right answer. That's how we're going to keep track of the acidity and basicity of things. There's no reason you couldn't have used pOH. It's just the opposite. 7 is still neutral, but a 0 pH is a really, really strong base, and a 14 pOH is a really, really strong acid. And all you do is, it's always just 14 minus whatever the other number is. So if you have a pH of 2, that's a pOH of 12. If you have a pH of 12, that's a pOH of 2. So you can think of it either way. We as a culture a long time ago decided that pOH was the right answer. Or, sorry, pH is the default answer. Okay. So just to keep things in perspective, it turns out that if you have a 1 molar HCl solution, or any strong acid, that's going to have a pH of 0, because the negative log of 1 turns out to be 0. Okay. A pH of 14 is a 1 molar like NaOH solution, so a strong base, KOH, NaOH, whatever. Okay. In terms of things that you might have interacted with, like stomach acid is kind of in this range. For what it's worth, your stomach acid is HCl. That's the acid that your body produces. It's used to dissolve food, totally useful stuff. But I will tell you, if you're ever in a lab and you have to interact with HCl, it tends to smell like puke because it's literally the main active ingredient of vomit. Sorry, kind of gross. If you have like a can of Coke, a pop, a soda, whatever term you use, I'm from the Midwest, so pop it is. Sorry if you're a soda person. You know, it's not much less acidic than than stomach acid. I remember when my kids were little, you know, one of them, they lost their tooth, and I told them, I'm like, all right, let's write a note to the tooth fairy. I will give you $1, or whatever the going rate was for a tooth at my house. And I was like, let's get a can of Coke and we'll throw your tooth in there and see how long it lasts. It didn't completely dissolve, obviously, but it did start rotting out because your teeth can't handle acidic conditions for very long. So it kind of trained them like, oh my God, this stuff is really bad for my teeth. Okay. You know, if you eat tomatoes, like fresh tomatoes, they're fairly acidic. Your blood apparently is just slightly on the basic side. There is a buffer system. We're going to learn how buffers work later. There's a buffer system to keep your blood pH from changing very much. It turns out that if your blood changes pH even a little bit, even half a unit in either direction, you pretty much die. So your body's really good at keeping it right around just a hair above 7. Okay. If you go to the store and you buy ammonia, like an ammonia solution for cleaning, it's a weak base, but it's a pretty high concentration. So it's over in the 10 range. Bleach, I'm going to run out of space. Bleach is more like an 11 or a 12, depending on, again, on concentration. but just so that you have some relative perspective on what these values mean. Okay, so the examples we did, you know, if you have a 0.0017 molar HCl solution, that's a pH of around 3. That's like kind of in this range. I don't know that my scale is perfect, but somewhere in this range. Okay, if you had a 0.00, what would that be? 0047 molar KOH solution, its pH is going to be like 11.7, which is all the way up here where about bleach would be. Okay, because bleach is actually a pretty weak base. We usually just use it in high concentrations. Okay, so, all right, thanks.